Our next speaker is Dr. Zachariah Uman. He is the director of the Forensic Science Program and a professor of forensic science at Albany State University in Albany, Georgia. His specialty is in forensic chemistry, forensic microscopy, fiber analysis, gunshot residue analysis, paint analysis, instrumental techniques, and forensic drug analysis. Today he's going to be talking about the instrumental analysis of gunshot residue and reconstruction of crime scenes. Dr. Zachariah Uman.
Good afternoon, everybody. Thank you, Ms. Sandra Coach, for your kind introduction. So my topic today is the instrumental analysis of gunshot residue and reconstruction of crime scene. It's not working. So today in the analysis of GSR, I talk about three instruments: scanning electron microscope, time of flight secondary ion mass spectrometer, X-ray photo electron spectrometer. And in the reconstruction, what I do is just collect the evidence from the scene, analyze it thoroughly, and then understand the relevance of the evidence to the case and the crime scene. So my objectives are what is gunshot residue, how does it is formed, what are the methods of characterization, the importance of GSR, learning outcomes, and finally some conclusions. So what is gunshot residue? As you know that when a firearm is discharged, you see as in the picture, you get smoke, vapors, other materials expelled in the area around the firearm. So the product of firearm discharge is called gunshot residue. Actually, it is coming from the cartridge. So it can also be called cartridge discharge residue. And so then the next question is, how does it form? When the firing pin strikes the base of the cartridge, so what happens is the primer and the powder inside the cartridge burns and turn into gases and come out along with the bullet. So those who are not familiar with this cartridge, let me say that so the cartridge consists of a bullet. It is located at the top. Then you have primer and other powder inside. So if you take it apart, you see the bullet. Sorry. So you can see the bullet and also the powder. Actually, the powder and the primer burns and you get the gunshot residue. So why GSR is so important? That is the next question, why we study GSR. As you know that guns are the most frequently used weapon for murders. More than half of the killings are because of the gun. And as you know that the gun industry has grown more than 150% in USA. It is estimated that there are 350 million guns are in circulation in USA, more than the population of US population. So, and it is estimated that there are roughly 33,000 gun deaths per year, that is 90 deaths per day in United States because of mass shooting, suicide, homicide. So it is so important to study. So what are the learning outcomes? You can first of all, by learning GSR, you can study you can determine the distance of the shooter from the victim. Also, you can find out whether the victim was alive before shooting, just noting the color of the GSR. If the GSR powder around the wound, if it is reddish brown and orange red, one can infer that the individual was alive before the wound was inflicted. And similarly, if you have a gray or yellow mark, you can say that the person was dead before shooting, and also you can whether the wound are occurred through the clothing, whether it is a suicide or a homicide, identifying the cartridge, that is very important. That means it is very important, it is very critical that whether the accused has fired the weapon. So that is very important. So these are some of the learning outcomes of the GSR. So then if we come to the I have some of the pictures just to look into whether it is a wound formed by the gunshot or by some other weapon, whether it is a suicide or a homicide, or the shooting distance can be determined by studying the GSR, and also it is possible to check whether the shooting has occurred from inside or outside of the window. And just it's for commercial break, let me show you this one, a picture. So here you see a frog, am I right? And so then now what you see? So just so this is just like forensic science, you have to be very careful in your observation. So are you in the right direction? So next is what are the methods of characterization of GSR? So once you collect the GSR, you have characterization, you can do it in two ways. Presumptive test you can do, similarly you can do the instrumental analysis. Presumptive you can do the lead test for lead as well as for nitrate ion. And the instrumental analysis, as I mentioned earlier, I have three instruments. Here you measure the morphology, topography, composition and mass of each components. And so reconstruction just to collect the GSR, characterize the components in the GSR. By characterizing the components in GSR, actually you are identifying the primer and the propellants. That means you are identifying the cartridge. Then it is possible to locate the identifier. So here, you can see some of our students are getting training for GSR, for firing and GSR collection. Actually, this we did in collaboration with Albany Police Department. So you can see that one of the officers is giving training to our students shooting and how does the GSR is collected from their hands. So collecting GSR from the, so actually we are collecting from this area. So that is where you collect GSR. So actually I have published some papers in the Journal of Forensic Science and also in Journal of Scanning Microscopies in 2006. So that have elaborate discussion of the gunshot residue, both lead-free primers as well as lead-based primers. So once we collect the GSR, actually we have to coat with gold. That is what I usually do when we have the materials in the aluminum stuff with the small materials on the, and this is placed in the carbon sputter coater, and it is coated with the gold. So even without coating with gold, you can do the experiment, but it is to get a clear experiment, so I do the sputter coating. Then I put it in the scanning electron microscope. In the scanning electron, this is the scanning electron microscope we have, and we study the topography, surface features, morphology, size and shape, and also we learn the composition elements and compounds. When we look for the particles, actually we are looking for the bright particles. Actually I am doing with inorganic gunshot residue particles. So we are looking for bright particles as well as the spherical particles. So we enlarge just the image, so make sure that we are getting a spherical particles. As you know that the gunshot residue, then the vapor comes out of the gun, it is high at a very high temperature. When it touches the cold part, due to surface tension, it assumes the shape of a sphere. So we are looking for spherical particles. So we get some perfectly spherical particles. That doesn't mean that we always get a spherical particles. We get some oval-shaped particles also. Once you have the particle, you analyze the size. You can measure the size. You can find the surface features, and at the same time, you can also find out the components present in this GSR particles. So that you can do by energy density X-ray spectrometer. So here is the energy EDS spectrum of the GSR component, and here you can see the lead, barium and antimony. Lead because of the lead stiphenate, and barium because of the barium nitrate, and antimony as antimony sulfide. Once you identified the particle, you can also find out the distribution of the particle among the components among the particle. That you do some hyperimaging, you don't have to do anything, just the software will do that one. Just assign different colors for this lead, barium and antimony. So by giving antimony a red color, so you can see that red color is spread all over the particle. Similarly for lead, you can see the green color, and also for the blue for barium. And also in order to get the for authenticity of the experiment, I just tried for carbon also, and you can see that the carbon area is completely blank. That means carbon is not present in that areas, only lead, barium and antimony. So once I do this experiment in scanning electron microscope, the same particle I can do it for a time of flight secondary ion mass spectrometer. I can put it the sample in the time of flight secondary ion mass spectrometer. Here is the instrument. Actually, we don't have the instrument. It is a very costly instrument. Actually, I did in collaboration with the Department of Chemistry in the Georgia Institute of Technology, Atlanta. And here we study the morphology, composition, and also mass of the components. That is one of the strength of this instrument. You can study the composition. So the other three, the surface feature, morphology, and composition, you can get from the scanning electron microscope. But the mass of the components can also be obtained from this time of flight. To give an idea about the fundamentals of the time of flight secondary ion mass spectrometer, so it is a surface analysis sensitive technique, and actually you are measuring the secondary ions produced from the sample, outermost surface of the sample. So once you have the secondary ions, you get the spectrum of the mass spectrum of the secondary ions. And also it is possible to obtain the map of any mass of interest where the chemicals are located. That is possible from this time of flight secondary ion mass spectrometer. So what actually you are doing is just sending some primary ions, the pulsed primary ions like Au plus or gallium, cesium plus or oxygen plus, to remove the outermost layer of electrons from the surface of the sample. This electrons that is or ions coming from the surface of sample or secondary ions, and the secondary ions are allowed to pass through a flight tube, and then you measure the time at which the secondary ions reach the detector. So you are measuring the time of flight. That is why the time of flight secondary ion mass spectrometer. And so it is possible to that by measuring the time of flight, it is possible to determine the mass of the component present in here. So it is possible to so mathematically we can show that the time of flight is directly proportional to the square root of mass over c. So you can as you know the particle, the kinetic energy can be equated to the charge of the ion or potential applied. Then the time of flight is the length of the tube divided by velocity. You can substitute velocity from the above equation, and finally you can show that time of flight is inversely proportional to the mass over c. So this is actually a schematic representation. You can see that so the sample here, the sample is here. You send the primary ions, pulsed ion primary beam, you get the spectrum. Once you have the spectrum, you can find out the map of that area of desired area. So if you want to get the map of this area or the spectrum of this area, you can get it. On the other way, if you first you get the map of the GSR sample, then from that map you can find out the mass from a particular area. That is one of the strength of this this instrument. So here is the secondary ion mass spectrum of a GSR, that is a Remington 22 caliber I did, and here you can see that you have the lead, the components are present, lead, barium and antimony present, the same sample that I did in the scanning electron microscope. And here you can see that lead, and so actually it is possible to say whether the components are present either in the elemental form or in the combined form. That is one of the beauties. So lead is present as lead and lead oxide, barium as barium oxide, antimony oxide and antimony. That is it. And it is also possible to find out the map of this. So here the picture is not so clear, but you will get the map antimony oxide, barium oxide, and this is the whole picture of this GSR sample. Then you have lead oxide and lead. I don't think the picture is not so clear. It is also possible to, this is the secondary ion images of before sputtering. So after the sputtering, we can also find out this. You get the same information, but you can see that, so it is not clear, but the information is that the amount of lead and lead present, lead oxide and lead present, the amount is slightly lower. The intensity of this picture is lower here in the case here. That shows that the lead concentration of lead and lead monoxide is more in the outer layer of this GSR sample compared to the sputtered layer. After we remove a 10 nanometer layer is removed from the GSR as received sample, so the lead and lead oxide concentration is less here. So that is the secondary ion mass spectrum. Then the same thing I can do with the XPS also. But actually, this is also a very costly instrument. The instruments look similar to that of a time of flight SIMS instrument. And again, we don't have this instrument. Again, I did with the Georgia Institute of Technology. So, so here in this topic, I didn't complete this experiment, but still I will share some of the points for academic interest. So what is XPS? How we can identify the elements and compounds, some of the examples. And what do you do with XPS? First, what you have to do, you catch the electron and identify it, and find out from which orbital it comes from, and find out from which atom it comes from, and then how many electrons are coming from a particular area, from a particular point. That is what we do with XPS. So, it is a surface analysis technique. It is qualitative, quantitative. You can detect all elements from lithium to uranium using this technique. It's a very simple technique and easy to understand. And the basics, just to say some basics about this one. As you know that the matter is made up of atoms, and the atom consists of nucleus and the electrons around it. And you know that each electron carry a ID with its address. The goal is to catch that electron and identify it. So how do you do that one? You have to expose the sample to the X-ray bombardment. Usually aluminum and manganese alpha X-ray can be used. That can remove the core electrons from the atom. Then once you have the electron from the sample, you measure the kinetic energy of the electron, calculate the binding energy, then plot kinetic energy or binding energy versus signal intensity. So that is what we do for. So in order to explain this one, I have a SPS spectrum for a palladium metal. So you can plot either kinetic energy over the electron signal or binding energy versus electron signal. So here is so we have several peaks here, and each peak represents an electron peak. So, and it also says that from which orbital that electron is coming. So this 3D is the 3D electron emission of the palladium metal, occurs around 335 eV. And also you can have the electron from 3s and 3p at a slightly higher energy level. And if you use a higher resolution spectrum of 3D, you can see that this 3D is again split into 3D 5/2 and 3D 3/2. And this is, that this 3D level is split into two because of the Russell-Saunders coupling, LS coupling. So 3D 5/2 has a lower binding energy compared to 3D 3/2. And again, this you know that this binding energy also depends upon the oxidation state and also the chemical environment. So this is one of the strength of this instrument. You can discriminate between the different oxidation state and chemical environment. So that, in order to explain that one, we have this titanium. So titanium metal and titanium oxide. This is in the +4 oxidation state. This is 0 oxidation state. You can see again you have 2p half and 2p 3/2 peak, and this binding energy of 2p is higher for +4 state compared to 0 oxidation state. But the chemical shift between 2p 3/2 and Tp½ is similar in both cases. So this is the actual, I have the actual, this is also not from my experiment, but for academic university. So this is the actual GSR layer XPS spectrum of here. So here you can see several peaks for lead, barium and antimony. Lead itself you have 1, 2, 3, 4 peaks are there. Similarly for barium and antimony. And this is the as received sample, spectrum for as received sample. And this is the sample after sputtering. And again you can see that the amount of lead present here is. So the lead peak is very high here, it is small. That means in the sputtered area, the amount of lead is small. So this is in confirming with the result that I got from the SIMS experiment. So these are my analysis of GSR with the different instruments, especially with the scanning electron microscope and SPS and SIMS. So just about the summary, SPS is a valuable complement technique for electron spectroscopy studies. SPS can provide important information regarding the surface composition and surface chemistry, especially for multi-component like GSR. So here I stop. If you have any question, that's welcome.